Okay, so let's speak about the first exercise in the first lab. So this exercise involves strings and proofs on strings. So usually when you prove things on strings, you're going to use induction, because most of the time we define a string recursively in this course, and proving things on recursion is the easiest to do using induction. Okay, so we are going to first assume that we have the length operator, right? So given a string W, cardinality of W is the length of W, and we define it recursively, which, is kind of silly, but bear with us. So if the string is empty, then the length is of course 0. Otherwise, if the string can be written as the AX, where A is a character, then the length of the string is 1 plus the length of X, which is hopefully natural. Now, we similarly have the concatenation operation, which takes two string WZ. And usually we either don't bother to write the fact that we are concatenating, it's just the invisible multiply operator, or we write a dot, or we write a big dot. Those are all equivalent. Here we write big dot in some places just to emphasize what's going on. Okay, so how do you concatenate a string? Well, if the string W is empty, then the concatenation is just the second string Z. Otherwise, W can be written as AX, where A is a character, and then it's defined as the concatenation of A with X and Z, right? And this is well defined because here what we are doing, we are concatenating a character to a string, right? And here we're concatenating two strings that are together shorter. So, so that this definition makes sense. Right? It makes progress. Okay. If you think about it as a recursive algorithm, it indeed would bottom out. Okay. So now, for the following exercises, we're going to assume the following lemmas. Let's go through them. They're all very simple and very intuitive, so in some sense they are obvious. So concatenating the empty string to a string W is equal to W. By the way, of course, the symmetric thing is also true, right? The second lemma says that concatenating two strings, the length of the concatenated string is just the sum of the length. Again, very natural. And the third thing says that concatenation is associative, right? You can put the parentheses wherever you want, which is also natural. Okay, next let's speak about reversal. So a reversal of a string is just to take a string and reversing it, right? So we are defining it recursively, because why not? Otherwise it would be too simple. So if the string is empty, the reversal is just the empty string. Otherwise, W can be written as AX, where A is a character, right? Here we're using the convention that A, B, C, and so on are letters of the alphabet usually, and the later letters in the alphabet are strings. Okay, so this is a convention. Try to keep it. It's a useful convention. Okay, so the reverse of such a string is, of course, the reversal of X concatenated with the letter A. Okay. So, for example, the reverse of stressed is desserts, and WTF 374 in reverse is 473 FTW. Okay, whatever that means. Okay, so we're asking you now to prove the following three things. So let's start from the first one, that the length of a string W is equal to the length of its reversal. Now, this is one of those things where, we have the intuition, you look at it and you should say, oh, well, of course it's true, but that's not a proof, right? A lot of things are obviously true and we still need to prove it. And a lot of things are obviously true and they're not true. So that's why we're doing the proof thingy, to really prove that something is true. So, and now the problem is, okay, how do we prove such a thing, right? So, I already told you the keyword here that we're using strings, so we have to use induction. And this is one of those cases where it's easier to just start writing it, see what happens, modify the argument, repeat until you get a full written proof. And maybe later on you want to take your proof and copy it and get a shorter and more elegant version, right? Because the nature of the thing is that when we speak and when even when we write for the first time something, we tend to be very repetitious and not necessarily very linear in our argument and very unclear and so on. And if you just do this with the proof, you will get a stream of thought, which might be a correct proof, but it might not be very elegant. So in general, I recommend that you write a proof and then you go over it and you try to shorten it. That's the way I write proofs, right? And in fact, it's true for any writing you do where it's not for personal consumption. You should always, once you wrote something, you should go over it and try to tighten the writing and remove unnecessary information in the proof. Okay, so let's go plunge in and prove this fact. So let me copy the claim, lemma, for any string W, in sigma star, we have that WR is equal to W. Okay, so proof. So let's write down what we already know. So this proof is going to be by induction. And the induction is going to be on the length of the string, right? So let's write it on the length n of W. Okay. Now, this is the beauty of induction. The base of induction is usually very easy, right? You just have to say, okay, this is the induction parameter and the length of the string. So let's handle the boundary cases, right? So base, which is, by the way, also the way you should write recursive code, right? First, you handle the boundary cases, and then you continue from there. Base case. And, in the base case, you're allowed to handle several values if you feel more comfortable with it. In this case, we just need to handle one case. If n equals 0, that implies that W is just the empty string, right? Now, if W is the empty string, what is WR? Okay, so for that, we need to go back to look at the definition. So let's do that. What is WR? Well, if W is epsilon, WR is just epsilon, right? To remind you, epsilon is just the empty string. Okay, so WR, maybe I should write the W bigger and the R smaller. So this is just epsilon R. This is just equal to epsilon, okay? And now we have what we want, right? The length of WR is equal to the length of epsilon, is equal to 0, which is equal to the length of epsilon, you don't say, which is equal to W. Okay, so that was the base case. Okay, now we need to write down the induction hypothesis. Okay, so what is the induction hypothesis? So the induction hypothesis can be, for example, so you need to look on our parameter, right? Our parameter is n, right? So induction hypothesis is going to be about n. Assume, and again, this is kind of, you can write this in some sense without thinking too much. Assume the claim holds for n smaller equal than k. Okay, so for some parameter k, for some. Okay. So we assume that the induction holds for some parameter k, and now what we do is that we need the inductive step. Inductive step. So assume w, the length of w, which is m, is equal to k plus 1. Okay. By the way, the assumption that the claim holds for all n smaller or equal than k, this is called strong induction sometimes. This is always the induction we will use. It never makes sense to use the weak form. A weak form is usually when you say, oh, it holds only for n equal k. But this is just a restriction that never makes sense. Okay. So back to our purposes. So assume that the length of the string is k plus 1, right? So then w can be written as ax, right? Okay, so then w reverse is equal to ax reverse. Now we need to look at the definition of the reverse operator. The reverse operator in this case says, oh, well, w of r is just equal to xr of a, right? So let's just copy this. Of a. Okay, so we have this, and essentially this is roughly what we need. Why is this roughly what we need? Well, what we really wanted to prove, right? Let me remind you what we want to prove. That's important to remember. We want to prove that the length, by the way, I wrote it wrong, the length of w and the length of w reverse is the same, right? Sorry for that. It's good that I fixed it. Okay, so the length of wr as such is equal to the length of ax reverse, right? Which what we just said is the length of xr a, right? Now we need to use whatever properties we have for the length operator. So let's go back because we could assume various things about the length operator. So one thing we could assume is this, that the length of a concatenated string was just the sum of length of the two strings. So let's use that. So this would be by lemma 2. And this is going to length of xr plus length of a. Okay. Now we're going to use the induction hypothesis, right? We're going to use the fact that the length of xr is equal to the length of x, right? Plus the length of a. Well, then a is a single character, so this is just 1, right? So this is equal to 1, and this is using the inductions, right? Okay. Now, in fact, I want to write it. Let me not do that way. Let me do it. Let me, in fact, keep the a. Okay. Now, summation is, I can change the order. So this is a plus x, right? And this, the length of a plus x, this is the length of the string ax, right? And here I'm using against this, what I'm using the length operator. I'm using essentially this, right? It's just that I reversed a and x when I used it, but it's still by lemma 2. I'm just using it now in the other direction. So this is still lemma 2. Okay, and now ax is of course equal to w. So this is the length of w. And we are done, right? Because we proved that the length of w reverse is equal to the length of w, and we write QED. And we celebrate the victory over the proof, or victory over the claim. So, so I hope you don't have too much of this feeling of what are we proving here? So I hope you understand what we prove, right? We are essentially literally proving that W of R is equal to the length of W. That's really what we are proving, right? And that's what the claim is, and that's what we are proving, right? And in some cases, when you don't know what is you're asked to prove, it's convenient to just formally write it down. Once you formally write down what you need to prove, it becomes clearer first what you have to prove and how to prove it. Now, I have another video where I go over how I think about induction. Let me do a quick review of this because I think it's important because I don't think people understand induction very well, or a lot of people don't understand induction very well, and people get fixated on the form because that's what they learned in earlier courses, and that's it. Okay, so the way I would like to think about induction, at least the simplest form of induction like we saw here, is that we have the integer numbers. 0, 1, 2, and so on, going all the way to infinity. Okay, not stopping anywhere. Okay, now we want to prove that the claim is correct. For all integers, for every n, the claim is correct, right? So now what our proof did? Well, our proof first we proved, think about here as literally having an array, a Boolean array, where we turn on a bit if we know that the claim is true for the value I, right? So then what did we do? First, we handled the case that n equals 0. We said, yes, this is true, right? And then what we did, we used the following idea. We said, okay, let's assume that n is equal to k. Sorry. Let's assume that we have value n and the claim is true, all the bits are on. The claim is true for all the values smaller or equal than n. Okay, so you can think about it is that the array is already full, and then we say, okay, what about the next entry in the array? Sorry, this should be k. What about n equal k plus 1? Okay, and then if you think about it, what we just did, we just proved that if all those bits before are on, then this is also on, right? And as such, this bit is on. And now as you think about it, this essentially implies that we can fill this whole infinite array. We could turn all the bits on. The claim is true for any values in this array. And this is really what inductive proof is, right? You're filling the array. Conceptually, you're verifying the result by an algorithm, right? And the proof, you can think about the proof as essentially a recursive algorithm that use the fact that the claim is true for smaller values to fill in the correctness for the current value. And that's how you climb from 0 all the way to infinity. So I don't know if this makes things any clearer, but that's the way I like to think about it. And hopefully it's useful. If it's not, my apologies. This is it for now.